Hello, it's Mr. N here, and we are going to be talking about an introduction to something called polar graphs and also polar coordinates, Polar, just like polar bear, polar coordinates, and also in general, polar graphs. All right, now what are polar graphs or polar coordinates? Well, it has something to do with something we've already seen before, this kind of grid. We've seen this kind of grid our entire math career, all right? And we actually technically call this grid a rectangular grid because everything is kind of square and rectangular, everything at right angles. We can plot points on it like the point 2, 3, or the point -2, -1, right? We learned all this in elementary school, middle school, whatever. So we're very familiar with the rectangular grid. And we've kind of discovered that we can draw lines, and as we've noticed, most lines tend to curve, parabolas, cubic functions, and all those ones that went up and down and did the John Travoltas and whatnot. It seems that most graphs tend to curve. And drawing curved lines on a rectangular grid, you kind of like, maybe there's something that we could use that's more suited to drawing curved lines. And there is, and that is called a polar grid. We're going to take this grid, which is all right angles and boxes, and we're going to substitute it with a round grid. And like this is what's called a polar grid. So all the rectangles and squares have been replaced with circles. So it's a whole new type of graphing. Now, where the two black lines meet, that's still the origin, just like these two black lines here. Origin is here, origin is here. That's the center of the graph. But instead of having squares, we have circles. So this is kind of like ring 1, and this is the second ring from the center, and this is the third ring, and the fourth and the fifth. And of course, the rings can radiate out forever. Right? This particular graph, we have 1, 2, 3, 4, 5 rings. So ring 1 through 5. We can have ring 6, 7. You can go as far out as you want. Just like with these graphs, the numbers actually go up forever. Practically, we only go to like about 4 or 10 because the graphs just get too big. So we usually stop about 4 or 5, just depending on the size of the graph. Don't worry about the colored lines right now, the pink and green. We're going to talk about that in a second. Just kind of pretend everything's the same color, but this is now there is no real X and Y anymore, not on a polar grid, right? Over here, when we graph, X was always sideways and Y was always up and down. Well, yes, you do still have a sideways and up and down, but we also have all these other directions you can go. Now, some of these directions should seem familiar. That's pi/6, this yellow line, and both of these yellow lines represent everything in the pi/6 family. Notice a 5 pi/6, 7 pi/6. A lot of we've seen those before, and now you're probably noticing the green lines are all the pi/4 families, and the red highlights are the pi/3 families. So they're just highlighted to be like, hey, those are angles you've seen before. And actually the black lines are 0, pi/2, pi, and 3 pi/2. So we've seen all those angles before. The only ones that are new is notice that there's now a pi/12, which we've never seen before, but pi/12 does fit exactly halfway between pi/6 and 0. And that's 5 pi/12, blah, blah, blah. Now, we didn't really know them on the unit circle. However, we have seen these pi/12 show up when we were doing the sum and difference formulas, right? We didn't know how to find the sign of pi/12 because it's like pi/3 plus pi/4. Actually, that's 7 pi/12. So by using different sum and difference formulas, we could find the pi/12s as well. I mean, it's possible. It's a lot of work. So we tend to kind of skip them, but they are there. And if you wanted to use them, you can. Generally, like 99.9% of the time, we're just going to focus on the lines I already know, which are marked in the different colors. The black lines, the yellow, the green, and the red. We're just going to focus on using those lines, although these lines are an option if you had a calculator or a lot of time on your hands. So a lot of graphs include them. Some do, some don't. Most do. So I just want to bring them to your attention. Okay, so this is what a polar grid looks like. And as you can see, it makes drawing curved lines maybe a little bit easier because the graph is already curved. So that's kind of the main reason that we have polar coordinates. Okay, now here's the thing. Everything that we were able to do on what we call now the rectangular grid, we can do on a polar grid. So this kind of means that everything you've started to learn about this, you now have to relearn how to do on this. So we're going to kind of take you back to middle school in that, like, how do you find a point on this grid? Now you kind of know that by now, but the question is, how do you find a point on this grid? Okay, so that's the first question. The first thing we're going to do is identify points. Now, I should have put something in your file, that this paper here with these notes, and we're just going to look at just this top half of how you find a single point. Now, actually, I'm going to tweak this a little bit. We're going to come back to that. All right. So in a rectangular graph, if you wanted to just mark a single point, you would call it the X and the Y. Points are called X and Y, where X represents the sideways number, right, how far you go left or right, you can also think of it that way, and Y represents the up and down number, right, or just U and D. All right, so between the two, it's kind of like Battleship. Between the two, you can mark any point on a grid. That's kind of like this. Now on polar, you can also mark just a single point. Like you could just mark this point right here, or just this point here, or this point here. Yeah, anywhere they cross, you can just mark a point. But there's no X and Y anymore. Or the two, you're gonna have two values, and two values are gonna be called R and theta. R and theta are going to be the two new terms we're going to use to describe them. Okay, so that's what I have written. I'm trying to show you right there. R and theta. R represents the ring that you're on. Remember how I said there's a ring? That doesn't count. That's just the origin. But this would be ring 1, ring 2, ring 3. So R tells us if R is 3. That means you're somewhere on ring 3. You're somewhere on this third circle. Okay, and of course you could be between them. You could be on ring 1.5, right? Just like how here you could be at the point 1.5. It's not marked, but you can still find that number, right? So same way here, you could find any ring. And there's technically ring 1.1. You could split this into 10. All right, so 1/2 or 1 1/4. You know, so any number you want. Typically, we just keep them whole numbers, but they don't have to be. They can be any number you want. You could have ring pi, which would be 3.14. So that'd be right about there, a little bit past ring 3. Okay, so R represents the ring number, and theta represents the angle you're at, because we did notice all these different angles. So like if you're at pi over 4, that's an angle. All right, so that would be, so if you're at the point 3 pi over 4, actually, well, I have some samples right here. Let's just go to them. So I'm going to take this away. All right, actually, we'll take this away for just a moment and we'll explain it. All right, so here's some sample problems. All right, and we're going to graph all of these points onto this grid. Okay, now here's what we do. Here are the notes for this, and I have this here. To graph a single point, you find the theta first, and then you go to the ring number. And we'll talk about if R is negative. I talk about the backwards. We'll worry about that in a little bit. Okay, so let's try to do this. Now, this is the point R theta. Graph this point. Find this point on this grid. Now, notice this time the numbers are not there. Sometimes the numbers are marked like they're here. Sometimes they're not, and you're just supposed to know. Okay, but you know, pi over 4 is always in the middle of these two. So that's your 0. That's your pi over 2. Pi over 4 is in the middle. All right, and then pi over 3 is just above that, and pi over 6 is just under that. So you can kind of still know where they are, right? So, you know, this is kind of the confusing thing about polar coordinates, even though this is what's written first. So yes, we are somewhere on ring 3. So it's center, ring 1, ring 2, ring 3. I'm somewhere on that ring. So you can go to the ring first, but I recommend it's actually easier to go to the theta first. So pi over 4 is this angle right here. Right, and on that angle, ring 3 happens at 1, 2, 3. There is the point, and I'll mark it in red. All right, that dot right there, all right, is where you would have the point 3 and then pi over 4. All right, I went to the angle pi over 4, which was this angle right here. All right. Remember, if we want to visualize it, it's this angle here. That's the angle pi over 4. It does, well, actually, once it goes outside, it's kind of 4 pi over 3, but it's all the same straight line. right? And then I go to the third ring out, 1, 2, 3, and that right above my finger, that's where I marked. It looks different here because it's a smaller grid, but that's what we're getting at. Okay, so that is the point 3, and then pi over 4. So let's try that again with this one. 1 and 5 pi over 6. All right, so now kind of confirm here, 5 pi over 6 would be right there. So that yellow angle there. So it's not the first one because that's 11 pi over 12, but the next one up, 5 pi over 6, would be right here, this line. That's where the line 5 pi over 6 is. It goes all the way through. Okay, so I'm somewhere on that line, right, from 5 pi over 6, and I'm on the first ring of that line, which is right, it's actually pretty close on this one, seems to be right there. So that is the point. I'll mark it in yellow as best I can. That is the point 1, 5 pi over 6, okay? All right, so I like to go to the angle first, find the angle, and then find the correct ring. So I know it's kind of done backwards. They mark the ring is always mentioned first, and the angle second. I find it easier to go to the angle first and then find the ring, but you could do it either way. It doesn't really matter, okay? All right, so let's go on to the third example, the point 0 pi over 12. Now, pi over 12, all right, you could actually calculate, figure out pi over 12 is a number small to 0, so that's right there, all right? So I'm somewhere along this line, and the ring number is 0. Well, the only ring 0 is the center. So that is ring 0. I'm going to do it in green, all right? So that, the origin, that is the point 0 pi over 12. Now notice, I wrote pi over 12, but if your ring number is 0, that could 0 pi over 2, 0 pi over 6, 0 pi over any, the angle actually doesn't matter if you're on ring 0. I could be on angle like, I don't know, 384 degrees. If this ring number is 0, it's just the origin, end of story. Okay, so when the ring number is 0, this number here, I'm gonna even cross it off just to say that it doesn't matter. That could be any number 0, and then any angle is just going to be 0. Okay, so hopefully that kind of gives you the idea of like how you could find some various points on the graph, because that's going to be part of your homework, because I'm going to give you some points and you're going to have to draw them on a graph. Even in Schoology you can do that. Sorry, the green doesn't show up very well there, but there you go. That is there right in the center of the green. Now let's talk about these ones. All right, now that was mentioned here in the notes. If R is negative, then you go backwards. So let's kind of talk about how that works, okay? So, and here in D, we have a negative R. Now, luckily, we still have the point 5. The angle is still 5 pi over 3. So on my graph, 5 pi over 3 is right there, this red one. So 5 pi over 3 is somewhere about here. That's 5 pi over 3. That line, okay? And normally I'd go to the second ring, but now 5 pi over 3, I'm gonna draw the whole line this time. Line 5 pi over 3 is this one. I'm gonna do it in red. This line is 5 pi over 3, okay? That's what that is. All right, but, and I'm going to 2, positive 2 would have been right there, 1, 2. But this line is a straight line, just like how we saw here. The line 5 pi over 3 doesn't just stop in the middle, it keeps going back here. So I'm going to keep extending this straight line all the way back here. All right, now this whole red line I'm drawing, that is the line that started at 5 pi over 3 and it goes all the way back. And the negative 2 means don't come forward towards 5 pi over 3, go 2 units away from it. That dot right there. Then I'm going to box that. All right, so boxed in red. That is the point negative 2, 5 pi over 3. Okay, so that's negative 2, 5 pi over 3. So I went to 5 pi over 3, drew that line, and then I went backwards. So that's what we mean by the note right here. All right, sorry, not that one. This note right here, go backwards. All right, so find the angle first and then go backwards. Now we're gonna do one more, and on this last example, notice this time the radian has been replaced with a degree. Because if you do recall, all these radians are degrees, right? Remember, pi over 4 is really just 45 degrees. That's 0 degrees. That's 90 degrees. That's 60 degrees. That's 30. So you could do these. Sometimes these are written in degrees as well. All right, so you can do them also in degrees. That is also an option, okay? So I would go to that 270 degrees. I'll do that in yellow. 270 is right here. That's 270. It's this line. It comes all the way straight through. And I'm going, so this is the line 270. Right? But I'm not going forward one ring. I'm going one ring. And remember, that line continues all the way through to pi over 2. And so one ring back is right there. All right, so there's my point. All right, and I'll kind of box that one. All right, so there's my point, -1 and 270. Okay, now by the way, it is also possible to have negative radians or negative degrees. And if this were negative pi over 4, hopefully we know negative 5 pi over 4 is right here. Right, it would just go back. So you could do that as well. So sometimes the radians or degrees could also be negative, but you would just go to that angle, right? So negative pi over 4 would be just going down. Normally we start at 0 and work our way up and around. And if it's negative, you start 0 and go down and around to get to the angle you want, okay? So you could kind of do that either way. Okay, so that is kind of a quick lesson on how to draw those points. There's lots of examples online on how to do that as well. But the next thing we're going to do is how do you convert them, all right? So yes, that's where these points are on this. Actually, you know what, before that, I just saw one other thing. We are gonna do one other thing, all right? We're gonna do some simple graphs, all right? Because the next step is you're gonna have to graph these. So since I already have the graph paper out, let's start now. Some of the graphs are gonna be very, very complicated, I'm not gonna lie, but we're gonna start with some of the easy graphs. And these graphs are actually 2 examples. There's 2 easy graphs, and I did 1 example of each of the easy graphs, okay? So I'm gonna use this grid, and we're gonna talk about how you graph the equation r equals 2, all right? So R, remember, stands for ring, so this just means ring 2, and ring 2 is just this one, and I just draw all the way around ring 2, and that is that graph, done. Ring 2, r equals 2 means draw and highlight ring 2. I could have r equals 3, then I'd highlight the third ring, or r equals 1. If r equals 0, that's just the origin. And so whatever number it is. Now if r is like 1.5, then you go between 1 and 2 and draw your own ring, right? Because these are just the integer rings. You could draw a decimal ring if you had to, all right? Now what if r is negative? Strangely enough, okay, so that's the interesting thing. So positive 2 is this way, negative 2 would be this way. If r equals -2 means you're going backwards, and it's still the same ring. So even if r is negative, still this. So even if I said draw r equals -2, this would still be my answer, because that means I'd go, instead of forward to 2, I'd go the other direction. I'd like back up. Imagine you're facing this way and you walk forward. Negative means you back up 2, and you still end up on the same ring. If I faced every angle and backed up, I'd still go on the same ring. So I'd still be at the same ring 2, whether it's positive or negative. It's actually the same thing, okay? So r equals any number is just gonna be a circle. So all circle graphs in polar are really easy and very straightforward. You just draw a circle around that ring. Now, the theta graph, theta equals, and in this case I wrote, it's hard to see, 7 pi over 6. Right, now 7 pi over 6, if I can find the paper, that is one of the angles we know. Right, 7 pi over 6 is, whoops, I'm spacing out for a second. Right there, I knew it was around here. All right, so 7 pi over 6, and it's just that straight line. And it does go all the way through. Like, the lines don't just stop at 0, it goes all the way through, you just continue all the way through. So you just find the angle 7 pi over 6, all right, which was right here, and just draw and go all the way through. Now it's a little tricky to find, right? You were kind of like not 1 but 2 below, so you're going to be 2 above here, or just get a ruler. All right, so that yellow graph line is that graph. That is the graph, right? 7 pi over 6. Theta equals 7 pi over 6. The graph of r equals 2 is this, and the graph of 7 pi over 6 is just this straight line that goes right through the origin. So if I had say theta equals pi over 4, I would just find 5 over 4 and draw a straight line through it all the way through the origin and beyond. That's it. They are all just straight lines that all go through the middle. Now you might be asking, is it possible to draw a straight line that does not go through the middle? It is. That's a little more complicated. We're going to talk about that in a future lesson. All right, but we're just starting with the simple ones. And if the line goes through the origin, it's just the theta equals whatever angle, and you draw it. So some of these graphs are quite simple. They do get more complicated in time, but that's where we're going to start. Okay? Now, what else do we have to do about these topics? All right, well, the next thing we have to do is know how to go back and forth between the two, all right? So if I draw a point on this graph, all right, and then I switch out the graph, where would the same point be on this graph? So if I draw the point 1, 2, and that's the origin, if I went 1 and 2 here, I'm not going to end up, it's going to be a different, the spot, it's the same location, but it's going to have a different name, right? It's kind of like if you're measuring something, the length of something, and you measure it in inches, and then someone else measures it in centimeters, you're going to get different numbers. It's the same length, but you're going to get different numbers. Well, if I do the spot 2, 1, and then I graph the spot 2, 1 here, it's the same spot, but it's going to have 2 different names. So how do I go back and forth between a rectangular point and a polar point? Okay, so there is a little rule there, right? And it's these two here in this worksheet. How do you convert rectangular points to polar and polar to rectangular? So these are the rules. Now, it's actually easier to just do it. So we're just going to write some examples, and then I'll show you that and how it works, okay? So first example, all right? Given a polar point, convert to rectangular. All right, so here's the point, the polar point, 3 and then 2 pi over 3. All right, so you could graph that point, all right, if I had to. I'm not asking you to graph it, but if you did, all right, the point 2 pi over 3 is over here, and the third ring out, 1, 2, 3. And so it's right there. But if you imagine that you put the regular grid lines over this and made it rectangular, this point, where does it end up on a rectangular grid? Okay, so that's what we're going to do. All right, so we're going to use this. We are converting polar to rectangular. So the rule is what you see right here. To find, so this is an R and this is a theta. I want to find the X and the Y. And so the X is going to equal R times the cosine of theta. So to find out what this X is going to equal R times the cosine of theta. Now in this case, R is 3, and the cosine of theta, and theta is 2 pi over 3. So that's 3 times the cosine of 2 pi over 3. Okay, all right, so then you just use your unit circle, all right? So 3 times, and the cosine of 2 pi over 3 is negative 1/2, right? And then 3 times negative 1/2, well, that's gonna be negative 3 over 2. So this point is going to start at the point negative 3 over 2. That's also the point negative 1/2. You can convert that from improper to mixed. I prefer the improper, but you could do it as mixed, and that would also totally be fine. Okay, so that is your X coordinate. And then, so you're just plugging them in. So you are going to have to know this formula. So have that formula with you. So that's how I found the X value. I had R, I had theta, so I just plug them in here, and that gets me the X value. To find the Y value, I'm going to do Y, the Y value equals R times the sine of theta, which makes sense, right? Remember I said Y's are with sine and R's are with cosines, right? So everything is just kind of making sense of what we've seen before. So to find the Y value, right, the Y value equals R times the sine of theta. Now R is still 3, and the sine of theta is 2 pi over 3. So I just work that out, all right? And the sine of 2 pi over 3 should end up being root 3 over 2. All right, and then multiply that together, well, that's 3 over 1. So it looks like I get 3 root 3 over 2. 3 root 3 over 2. And this is the polar version, and this box here, that is the rectangular version. All right, so if I want to find where this point is, if that's where that point is on polar, that's where that same point would be on a rectangular grid. Okay, it's like converting inches to meters. It's similar, except we're going from a polar grid to a rectangular grid. They both mark the same point, but they measure them in different ways. This is like inches to centimeters or vice versa. Okay, so we're just kind of seeing the same, where does the same point end up? Yes, so that's one example there. We'll do a couple more. Okay, so similar example. So kind of memorize this formula that R equals cosine of theta, that's a theta, and Y equals R times the sine of theta. All right, so that's in your notes. All right, so same thing. Let's say we're given the polar point -4 and 5 pi over 4. That's the polar point. All right, convert this to rectangular. So this is R, and this is theta. All right, that's a theta. So convert this to its proper X and Y points. All right, and we're going to use these formulas right here. All right, so to find the X value, X equals R. In this case, R is -4 times the cosine of 5 pi over 4. All right, and let's work that out. That's -4 times, and the cosine of 5 pi over 4 is -√2 over 2. Now, 4 is over 1, and first of all, the negatives cancel, and then 2 goes into 4 2 times. So it looks like my X value is going to be 2√2. So that's my X value of the point. I still got to find the Y value. Okay, so the Y value, use this formula up here. So Y equals R, which is -4, this time times the sine of 5 pi over 4. All right, well, -4 times, and the sine of 5 pi over 4 is also -√2 over 2. And that's the same thing, right? The negatives are going to cancel. 2 goes into 4 2 times, and we turn out to get the same point. Now, sometimes that whoops, 2, not 3. All right, now that doesn't always happen. It didn't happen up here. Usually they're different. Because it's pi over 4, anything pi over 4, they usually do turn out to be the same, or a sign might be different, but it's the same answer. Because pi over 4, you're on the diagonal line. All right, you're on these diagonal lines, right? The green ones. So green one, if you're graphing it rectangular, it's like 2, 2, or 3, 3. It's always the same. So kind of similar, kind of makes sense that they should be the same value if you're on any kind of pi over 4. Of course, they could be negative, right? This point here, right, that could be like -3, +3, or something like that. But they're still the same numbers, just different signs. All right, so that's pretty typical for that. Okay, we'll do one more, and then we have a little catch. So one more example. Let's take the polar coordinate, 7, and then 90 degrees, because usually it's written in radians. Usually we have radians, but sometimes we do degrees. Remember, because degrees and radians are the same thing. So where's the point? 7, 90, that's the polar. Where would that end up on a rectangular grid? Okay, so same thing. I need to find X and Y, because that's R and theta. All right, so R, to find the X and Y version, X equals R, which is 7 times the cosine of 90 degrees, okay? All right, well, the cosine of 90 degrees, last I checked, is 0, right? Cosine of 90, whoops, you can't see that, let's move that up. Cosine of 90 degrees is 0, so that's just the point 0. So the X coordinate is 0. It's 0 comma something. That's the X value, right? The Y value I'm gonna find by doing the same thing. Y equals 7 times the sine of 90 degrees, and hopefully use your unit circle if you need to, but the sine of 90 is just 1, which is 7. So that's the point, 0, 7. Now this one should hopefully make a little more sense when you see the two different grids. And let's see if I have both grids. But you can kind of visualize, right? In polar, boom, 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 you go to the 7th ring and 90 degrees is up here. But in rectangular, you go to sideways none and up 7. Right? And so they kind of are the same point, because the 7 rings is similar to like how many units you're going up. So it is the same point. 7 rings up at 90 degrees is the same thing as 70 up, all right? And so if you're over here in polar and over here in rectangular, this would be pi, and this would, So you can kind of see how some of these kind of are the same point with different names. Maybe you don't get the last one, but if you get this one, that's actually pretty good to me. All right, I'm actually pretty happy with that. Okay, now, so we're going to go from given rectangular, convert to polar. Now this has a couple extra catches. So, all right, so here we go. So given this point, 1 square root of 3, convert that to something. So that's in the point x, y. Now, y can't be root 3, right? Because square root of 3, use a calculator, it's about 1.7, right? So take the, so this would be like a 0.1 and 1.7, and convert that to something in r theta form. Now, there's a couple catches you need to know about this one off the bat. All right, first of all, before you got to start on this, you didn't have to do this on the other ones, but to go from rectangular to polar, you kind of want to know before you get started what quadrant you're in. And on a rectangular grid, if you're on a rectangular grid, the point 1, 3 would be in quadrant 1, right? If you're not sure, I'm not sure if I still have that grid handy. But anyways, yeah, that would be in quadrant 1, right? 1 and then up 3, that's up here, that's somewhere up here. So you're in quadrant 1. That's going to come in handy because later on you're going to need to do some inverse trig stuff, and you have to know which quadrant you actually end up with when you do the inverse trig stuff. Okay, all right. So whenever you do your thing, make sure you're in quadrant 1. Okay, so here's what we need to do to solve this. We're doing this, we're converting rectangular to polar. So we have x and y, we're looking for r and theta. To find r, you do this with x and y, and to do theta, you do this with x and y. Let's write down the r1. The r1 equals square root of x squared plus y squared, which should look vaguely familiar. That's a little bit like the distance formula and a circle. All right, kind of similar, but there you go. All right, so to find r, plug in x, square root of 1 squared plus y squared, which was square root of 3, right? And now just work that out, right? 1 squared is 1, square root of 3 squared, so squares and squares just cancel. So it's just 1 plus 3, which is square root of 4, which equals 2. Now, I'm going to tend to use a positive one. Technically, it could be negative, but usually we just use the positive one. We're not solving an equation. That's when you have to do the plus or minus. We're not really solving a full equation here. Although there are times when the negative one comes in handy, but when in doubt on these, 99% of the time, the positive one is going to work. So I would just stay with the positive one. Don't worry about a negative answer, even though we took a square root. Okay, so that means my r is 2. Right? So that means that this point would match ring 2 on a polar graph. I'd be somewhere on ring 2. Now, where on the ring am I? Like at what angle? Well, I use this formula to find the angle. Theta equals, I know my thetas look like A sometimes, the inverse tan of y over x. And this is why we learn inverse tan formulas, okay? So plug all that in, because you know x and y. So inverse tan, because they're right here, x, y. So inverse tan of y is root 3 over 1. And you could reduce that, but it's actually a little easier to keep it like that on your unit circle. Now, actually, if you really think about this, there are technically kind of 2 places this could happen, because tangent is positive in the first quadrant and in the third quadrant. Right? Tangent is positive because this is a positive number. It's in positive in quadrant 1 and 3. But remember, that's why I checked up here. The angle I want is in quadrant 1. So I'm going to use the quadrant 1 angle that's there, and that turns out to be pi over 3. All right, so that's my answer, pi over 3. Now, if this had been negative, and if it had been in quadrant 3, I would have found the quadrant 3 version of this angle that would have worked, and that would have been 4 pi over 3. Okay, so that could work. So that's my final answer. Now, before we do go on too deep, all right, so if I did graph that, you don't have to graph that, I didn't ask you, but I'm going to graph it to make a point. We are done. That's my final answer, but I have to bring up something important. Now, if you graph on a polar grid, there's ring 1, there's ring 2, and pi over 3 is about here, okay? So that is the point we're talking about. That is this point, right? And that is the point, right? Ring 2, pi over 3, that's it. There is another way to describe this point. And I did say take the positive. I did say you could take the negative version if you wanted. Now, if you took the negative version, you'd be here. And this angle would be 4 pi over 3, right? But if you want 4 pi over 3 backwards, you'd end up in the same spot. So you could also call this the point -2 4 pi over 3, right? So if you use a -1, use the angle across from the angle you wanted, right? Because 4 pi over 3 is opposite, and so instead of going 2 units forward, if we went 2 units back, you end up on the same spot. So either of these answers work. There's actually more than one way you can describe a point in polar coordinates. In fact, there's an infinite number of ways to do it, because also you could take the same point and go around the unit circle and add 2 pi to that. So if you had pi over 3 and added 2 pi, I think you would get like 13 pi over 3. And that would be another way to describe this point, 2 and 13 pi over 3, because you could just go all the way around the circle and end up at the same spot. And if you go around the circle, you're adding 2 pi to the angle. So if you did pi over 3 plus 2 pi, I get a common denominator, and that's going to be 7 pi over 3. So this is also the angle 7 pi over 3. So this could be the point 2 and 7 pi over 3. And that is also another way. So there's actually, as is going to turn out, an infinite number of ways to write polar points. For any one point, there's an infinite number of ways of writing it. Because I could have also subtracted pi over 3, because I could have gone back 2 pi. Or I could go around, instead of going on 2 pi, I could go around twice and add 4 pi to this. They're all going to be usually over 2 or -2. That really can't change, but your theta can change a lot because you can keep adding them. If you don't get that part, that's fine, but the big idea is make sure, and if you only get this, that's also totally fine, but I want you to be aware that there are multiple ways to describe this same point, okay? All right, let's do one other example, at least, maybe 2. Okay, so we're still doing the same thing, okay? We're given a rectangular, let's convert to polar. So this time, let's give you the rectangular point, -5, 0. Now that would be pretty easy to graph on a rectangular grid, the point -5, 3, 4, 5, 0. All right, that's on an X and Y grid. All right, that's how you would graph that point. How would you describe that point on a polar grid? Now, once you see that, you actually might know, but let's still use these formulas and confirm it. All right, here's my X value, my Y value. Let's do it as R and theta, but I need to find out what R and theta are. And let's do it with the formula. So R equals the square root of the X value, -5 squared, plus the Y value, which is 0, right? Y is 0, and 0 squared is just 0. So R equals the square root of 1, because -1 squared is 1, and that's just 1. Okay, I was saying not 5, these are 5s, not 1s, my bad. So -5 squared is 25, and the square root of 25 is 5. Okay, so that's what R equals. R is 5, so that means I'm on ring 5. And the theta, now I actually can probably guess, but let's do the calculations and prove it, because we already know in theta that's probably pi. But let's do the formula and see if that works out. Okay, so theta, because we already drew a sketch, so we kind of sort of had an idea. The sketch doesn't always work, but it does kind of work this time. All right, so theta is supposed to be the inverse tan of the Y value, 0, over the X value, -5. Well, that's just the inverse tan. 0 over 5, -5 just reduces the inverse tan of 0. And where does the inverse tan equal 0? It happens at pi, which is what we suspected, because this is pi. So I'm in the 5th ring at angle pi. So there is your angle. All right, that's not the only way to write it, all right, but that's the main way. All right, so that's your main answer. Or you could go to 0, ring 0, and go back to -5. So you could do -5, 0. That's another way to write it. That would also be considered true, all right? Or it could be the 0.5, and you can add 2 pi to that and get the 0.5, 3 pi. That would be another way to write this point, because you would go all around and end up in the same spot. So that would be from pi plus 2 pi is 3 pi, right? And that could go on forever. So 5 3 pi. You could do 5, 5 pi, 5 and 7 pi. Keep adding 2 pi to it. You could also be subtracting 2 pi. You could do the 0.5 and negative pi, right? Because pi minus 2 pi would be negative pi. So all of these are all possible answers. You only need to find one, and I think it's easiest to just find the first one you get from the formula. And this one, notice I didn't talk about what quadrants it's in, because it actually wasn't on a quadrant. It was kind of between quadrants. So there was kind of no point in guessing which quadrant it was on. Okay, we'll do one more example, because this does tend to be a little bit trickier. So let's do one more final example. So the next one we're going to do is we're going to convert the point -1, 1, that rectangular coordinate, x and y, into its theta, right? Something in r theta, r and theta. Now, this one, if I did a quick sketch, the point -1, 1 is in quadrant 2. All right, this is in quadrant 2. I didn't worry about it on the second example because it was on the line. If it's on the line, then it'll just kind of work itself out. But this is in quadrant 2. So when I get to the inverse tan function, I'll have to pick something that's in quadrant 2. All right, so I already know that off the bat. Okay, now let's find r. R equals the square root of the x squared, so -1 squared, plus the y squared, 1 squared. All right, well, -1 squared is 1. 1 squared is 1. That's the square root of 2, which does not simplify any further, but that's okay. All right, r can be, it doesn't have to be an integer. It can be square root of 2. Remember, if you did square root of 2 on a calculator, it would be about 1.14. So you can find ring 1.14. Right, that's not a big deal. So that's totally okay. So there's my r. Let's go to the theta. Right, theta is the inverse tan of y. Y is 1 over x, -1. Now that does simplify to the inverse tan of -1. Now let's think about that. With all students take calculus, that's where things are positive and negative, right? This tangent's negative, and tangent being negative can happen in quadrant 2 or 4. It could happen in either spot, right? But because I already know that this angle is in quadrant 2, I'm going to want the quadrant 2 version. So I'm not going to use the quadrant 4 version, because it does happen. The tangent equals -1 in quadrant 2 and 4. But I need the quadrant 2 version because that's where the point is located. So the quadrant 2 version of tangent of equaling -1 is 3 pi over 4. Because tangent also equals -1 at 7 pi over 4. But 7 pi over 4 would put me in quadrant 4, and I need to be in quadrant 2. So I'm using the quadrant 2 version, so it's 3 pi over 4. So that is my final answer. Now again, we're done. There's other ways to write that, all right? But one, I'll leave this for you to figure out. You could also call it the point -√2 and negative pi over 4. All right, that is another possibility. I will leave that for you as an exercise to kind of determine how you know that works, but there you go. Okay, so we've been doing a lot. All right, we've learned how to graph points and do simple graphs, and we've learned how to convert points. All right, so this worksheet here has everything to convert rectangular polar. Use this. If you have a polar point and you go to rectangular, you do this and you just plug them all in. Okay, so hope that helps you out, and good luck, everybody.